going to be talking to you today about modeling a refuge room using CSA F280 standards. So I'm going to talk a little bit about the BCBC requirements, a couple comments about the CSA F280 standard itself, and then we'll jump into an example of modeling a 26-degree refuge room. We'll talk about when cooling is required. I'm going to make a few comments on what I think some of the future amendments are going to be. And then at the end, we'll save some time for Q&A. The BCBC requirements. So heating and cooling equipment is to be sized using CSA F280 standards. That is the only standard referenced in the code of Part 9 for sizing heating and cooling equipment. The design temperatures are prescriptive. So that's the indoor temperatures and the outdoor temperatures that are to be used. And this is the new clause that's causing a whole bunch of confusion. One room has to be able to maintain 26 degrees C. So this is the code clause in 933 that says the capacity of heating and cooling appliances has to be sized using CSA F280. Before the 2024 BCBC rollout, it only applied to heating, but now it applies to both heating and cooling appliances. And this is the sentence that deals with a refuge room. So it says, at the outside summer design temperature, required cooling facilities shall be capable of maintaining an indoor air temperature of not more than 26 degrees C in at least one living space in each dwelling unit. So there's a lot of confusion about what the CSA F280 standard actually is. And basically, when you get right down to it, it's a calculation method for heat loss and heat gain. Okay? It's for selecting heating and cooling equipment. It applies to Part 9 buildings only, and it has no comment on the distribution system or installation practices or anything like that. So all it's going to do is give you the ability to output a peak load. And so it was also designed with the intent to determine the heating and cooling capacity of the whole dwelling, not just for a single room. Now, we've been asked to apply this to the refuge room, but we don't have a clear set of guidelines, and CSA F280 was never really designed with this intention. So we're going to have to make some assumptions in order to create an accurate model. And I actually have a meeting about this next week with the Building and Safety Standards branch. TECA and HVAC DC are going to try to put together a guideline for the proper way to model a refuge room, because right now we feel there's a lot of inconsistencies when everybody's making their own assumptions, and there's not clear guidelines. So we also want to provide a bit of cover for our designers so that they have something they can fall back on and say, I have done this to the proper standard. So looking at CSA F280, so we always have external loads, and this is mostly what people think about when they think about heat loss and heat gain. So they're considering the conductive heat transfer through the building, solar radiation, ventilation, and leakage. But in addition to that, CSA F280 has this requirement for considering internal loads. So each occupant, you have to allow 240 BTUs per hour per person. And then for like an electrical load, at a minimum, you have to provide 2,730 BTUs. If you're over 2,150 square feet, you have to apply 1.27 BTUs per square foot. So let's look at a heat gain example here. So I pulled this example from the appendix of CSA F280. This is a 3-story house that's about 3,000 square feet. I set it in Vancouver, BC, so the summer design temperature is 28 degrees C. I've applied the net zero building assemblies, so this is a very high quality installation. We have very high quality windows, lots of installations on the walls and the ceilings. And we have 5 occupants, an HRV running with 110 CFM, 82% sensible efficiency, and the windows have not been shaded at all. So taking a quick look at the basement, this is mostly below grade. It's about 1,000 square feet, and it only has a heat gain of 145 BTUs. So this really highlights the foundations are, below grade elements are basically ignored in CSA F280. The only amount of heat gain is really coming from the two northern windows. So the main floor, we got about 10,000 BTUs. Seems, you know, proportionally quite high compared to the basement, but we'll take a look at why some of these loads are coming in a little bit higher. And then we have on the top floor about 4,000 BTUs. Okay, so looking at a sheet here, the heat gain for the whole house is about 14,000 BTUs. Now I set the indoor set point temperature to 26 degrees C. Typically CSA F280 actually specifies 24 degrees for indoor air temperature. So we're looking at 13,659 BTUs total. So that's sensible and latent. Now, the way CSA F280 calculates latent loads is it takes the sensible load and it says, well, your latent's going to be 30% of that sensible load. Okay, so every time you get an output down here, sensible, you times that by 1.3, that's going to equal exactly this sensible and latent load. So a couple things to consider here. We have very high quality walls and ceiling assemblies, so we're only talking about 200 and 660 BTUs for the walls and the ceiling. And compare those values not with the total, with the sensible, right? Because all of these values are going to be added together into the sensible and then multiplied by 1.3. So looking at like 200 BTUs compared to 10,000, that's not a lot, right? It's peanuts, basically. There's nothing from the floor. The windows are 4,041 BTUs, so that's about 40% of your load. Our leakage is only 88 BTUs, and ventilation is 285. So those are also relatively low. But now we come to these interior loads. 5,218. That's substantial. You know, that's almost half of our sensible load right there. So between the windows and the interior loads, that really is the majority of this number. So when we're looking at how to model a refuge room, this is my opinion, because as I mentioned, there is no set of standards. So these are the guidelines that I follow. I calculate the heat gain on a single room only. So what I do is I take that room and I model it as if it were its own independent structure. And then I take all of the interior surfaces and I assume that they are at outdoor design conditions. I'll include all of the occupants in the dwelling in that refuge room. I'll assume a minimum electrical load of 2,730 BTUs. And then we'll apply the 26-degree indoor set point temperature per the code requirement. Personally, I would recommend that when you're doing heat gain calculations, you at a minimum follow CSA's guidelines and do it to 24, if not lower. But the code allows for 26, so we're going to look at 26 just so that we can have an even comparison here. So let's look at making this living room a refuge room. So that's this one down here in the southwest corner. So I'm going to take this section of wall and this section of wall, and I'm going to say those are exterior walls and this is outside space. Okay, now that seems pretty drastic, but as we saw from the previous spreadsheet there, your window loads or your wall loads aren't very much when you compare them to the windows and the interior loads. So this looks kind of extreme, but it's actually not a huge change. And then above this space is a bedroom. So I'm going to treat that above space as if it were an attic. Now, in this case, I omitted adding the floor because it's a below grade basement and the entire heat gain section was like 145 BTUs. So I didn't feel that was appropriate to apply. If there was, say, an above grade element below, I'd probably just take the R value of the walls and say, I've got that on my floor, and then the floor is an exposed floor. I took the entire ventilation load and put it in that small space. I put all 5 of my occupants and then the electrical load. So what does that look like? Well, on my right here, this is that same table of the whole house. So we had 2,738 BTUs for the living room when we're looking at a model of the whole house. Now, when I'm looking at the living room as a refuge room, it jumps up to 6,816. So what are the changes? If you look at the walls, they go from 29 BTUs to 47. You know, percentage-wise, that's a huge increase, but when you're looking at the overall load, it's actually negligible. There's now about 100 BTUs for the ceiling, 0 for the floors, because I omitted them. The window load is exactly the same. The leakage has gone up, 3 times, but again, it's only 35 BTUs. That's nothing. And then the ventilation load has increased substantially, but it's also relatively low, 425 BTUs compared to 5,241. You know, we're talking below 10% here. And this one I think is maybe the easiest one to dispute me on including, because that is pretty drastic to include all of that ventilation in the very small space, because you can see that it actually jumps up from our total ventilation load, which was like 285 on the whole building. It jumps up to 425 when you cram it all in one room. But again, that load is so small, you know, I'd rather just include it to be able to tell somebody who questions me that it's included in the calculation, rather than trouble explaining it. But now you'll see, here's the big difference. This internal load is 3,924 BTUs. So when we modeled the whole house, the electrical load and the occupant load was split between 4 rooms. So the living room, dining room, kitchen, and family room, I believe, had an even split for all of those internal loads. And the total was 5,218. So now when I've put it all in one room, it's dropped to 3,924. And the reason for that is because I've adjusted the square footing, right? So this was a 3,000 square foot home, so it triggered that 1.27 BTUs per square foot. Now that we're dealing with, say, 280 square feet, it just hits that minimum 2,730 BTUs. So our sensible load is 5,243. We times that by 1.3, and we end up with 6,816 BTUs for our refuge room. So if it were me designing just a simple system, I found this on the old Samsung website, 9,000 BTU unit. So this is a 3/4 ton unit. Easily meets the 6,816 BTUs. Now, there are probably smaller units out there, but do keep in mind that the code and CSA also specify that it has to be an installed appliance. You can't use a window shaker or a portable unit. It has to be installed. So this is the smallest one that I found for them. Easily meets this 6,816 BTU load. So when we're making this decision to select a refuge room, just keep a couple things in mind. So it has to be a finished room. You should consider passive cooling strategies. So in my own home, one of the methods that I use to control the heat is I close off certain doors when it's really hot. I drop the shades, and that allows me to actually get away with a very small amount of cooling for my floor plan, because I'm controlling some of those heat gain loads. Okay, but now we're moving past the bare minimum of code compliance and getting to the point where you as a good designer are adding value. So a 3,000 square foot home, I think in most cases you'd be looking at air conditioning throughout. However, you know, some systems, some people for whatever reason might not want to do that, and you might be put in this situation. So if I have to provide cooling in here, I want to put it in the best location possible. So I'm going to think about occupant comfort and how this piece of equipment is going to improve the performance of the building as best as possible. So after I've completed my calculation on this living room, I'm going to take a beat and think, is there actually a better space for this refuge room than this living room? And in my opinion, yes, there absolutely is. So I'm going to rerun the calculations looking at the family room, kitchen, and breakfast nook, and see, can I take that same piece of equipment and just move it to a better location? So we all know, like, when somebody's using their house as a common practice, you're in the kitchen a lot, right? So my client's probably not going to be thrilled if the only cooled room is in the living room and they're bouncing back and forth to the kitchen to grab a cold drink, you know, in a heat wave or something. So let's see if we can pick an area that's like twice the square footage, and if we can still use that same piece of equipment. And the answer is yes. It might be a little bit surprising because that space is so much bigger, but when you think about it, it makes sense, because sure, our wall and our ceiling and potentially our floor loads are going to be higher, but they're small. They're small anyway. So increasing them, you know, doubling them is still not a huge gain, because really so much of it is coming from this interior load. You know, our windows have gone up, and if you look at those 3 rooms, you'll notice there's a lot more window space there, but they're all pointed north. So, you know, that's something to consider too, is the orientation of the refuge room. A north facing room is always going to have a lower load, especially on the windows. So really what I'm getting at here is leakage is the same, ventilation is the same, interior loading is the same, and that's the majority of the load. So we can move that same unit to the kitchen, family room, and breakfast nook and provide a whole lot more thermal comfort. Same equipment. So you might ask, well, if the load's so small in the basement, why don't you just use the finished basement as a refuge room? And the issue here is, well, you're still going to have to move those internal loads to comply with CSA F280. And I would argue that your occupants are not going to get a lot of comfort out of this, because we know it's going to be cool down here anyways. I don't see a lot of people using an entirely below grade basement, turning on the air conditioning there, right? And you're going to have to put it in anyways, realistically, so you might as well put it somewhere where it's going to add value. When is cooling required? Because I think there's a very strong argument here to say, well, that basement is already going to stay at 26 degrees C. But the issue is, how do you prove it? And I don't have a good answer for that, I'll be honest. It's a very difficult situation, because I feel like some of the decision makers had an expectation that CSA F280 can provide a very clear yes or no answer if cooling is required. And CSA F280 will always return a value that says some cooling is required. And there's no mechanism to apply that says, well, if it's less than 4,000 BTUs, you're fine. You don't have to worry about it. That doesn't exist in CSA F280. So without some sort of mechanism to say how little is enough to ignore, you're kind of left in this no man's land of, well, I have a cooling load and the code says I have to provide cooling. And so you end up basically getting tied into providing cooling. The other thing to consider is that although CSA F280 provides some measures for passive cooling strategies, including overhangs and shades, it never allows for a passive cooling approach of, say, opening a window. So let's take the same house and let's move it to some other locations. And the one I really want to highlight here is Alert in Nunavut. And the summer design temperature in Alert is 13 degrees. But we're still getting a heat gain of 5,382 BTUs. So when you look at the breakdown in alert, some interesting things happen. So we have no loads from the walls. So we don't get credit for that outside temperature actually being below our set point temperature. It just zeroes that value. The ceiling is very small. I assume that's due to some amount of solar radiation built into the calculation. Same with the windows, because there's not going to be any conduction, because the outside air temperature is lower than our indoor air set point temperature. Now you look at the leakage in the ventilation, and something interesting happens there. You get a negative load. So it's saying, yeah, actually we're getting cooling due to leakage and ventilation. But we still have the same interior load. And you'll notice that is the exact same interior load that's in Vancouver. And that's going to be true in Toronto, take your pick. Every single city, wherever CSA F280 is applied, that same square footage home is going to, with the same number of occupants, is going to have that same internal load. And that blows up our whole calculation here. Because you can see the sensible load actually drops lower because of our free credit on the leakage and ventilation. But then you times it by 1.3 and you're already up to about half a ton of cooling. Why does alert need cooling? Why does it need cooling? It's really frustrating because, well, for one thing, alert, they're on permafrost, so they don't actually have fully submerged basements. Regardless, what CSA F280 is saying is you need half a ton of cooling in there, and it isn't very logical, right? Because what do you do when it's 13 degrees outside and you're hot? You open a window, right? And this is the sort of climate where you can absolutely do that and regulate your heat gain just by passive measures. But we don't get credit for anything like thermal mass. We don't get credit for opening a window. The below grade elements, radiation pulling heat off of you has a huge cooling effect. You don't get credit for any of that either. Because all CSA F280 is going to do is provide you a peak load. And you might ask, why? Like, that seems weird. Why? Why would it do that? Because that's what it was designed to do. It was never designed to answer this question of, is cooling required, yes or no? The best piece of information I have on this is this Building and Safety Standards Branch information bulletin. So they released this in April 19th, 2024. I highly recommend you read it if you haven't already. And it mentions things like passive cooling strategies, which is really mitigation for your cooling load. It mentions you're supposed to use CSA F280, not HOT 2000 for your energy modeling. And it does explicitly state that passive cooling is allowed. Namely, in this sentence where it says, designers in Part 9 buildings are required to provide sufficient information to demonstrate that a minimum of one living space in each dwelling unit meets the 26-degree indoor design temperature requirement through passive and or active measures as per CSA F280. But as we've just seen, there is no method for showing that a passive system is acceptable through CSA F280. It also will point you to this clause in the code in Division C that says, sufficient information shall be provided to show that the proposed work will conform to this code. But there's no explanation of what you are required to provide to show this information. So what do you need to provide in order to show that cooling is not required? And this is my feeling. Because as I mentioned, there's no guidelines, there's no explanation. I think you need simulation data because you're going to have to look at this time element that CSA doesn't have at all, right? As I mentioned, this is peak load. So it cannot model the propagation of heat through the building. So you're going to need weather data. You're going to need the thermal mass of the building. You're going to have to model that propagation of heat transfer through the building. And that is extremely complex. Like, there's a reason that CSA F280 runs the calculation the way it does. It is explicitly to avoid this kind of math-heavy calculation. And really, at the end of the day, it puts you in the spot where you essentially need an engineer, because you have to show like an alternate pathway to code compliance. And it's really difficult, because I know that some of you designers out there are going to take one look at some of these below grade rooms, and you're going to say, well, there's no way this is ever going to hit 26 degrees C, but you're put in a very difficult position, because how do you prove it? And that's like, you know, and that's kind of where I'm at right now on this discussion. There are a lot of talks on this because these concerns have been highlighted. The National Building Code, there's a committee looking at adopting this refuge room clause, and I actually gave a presentation to that committee not too long ago and highlighted the same issues that I've highlighted today, that CSA F280 does not have the ability to answer, is cooling required, yes or no? So my feeling is they're going to probably make some modifications to that wording before the National Building Code adopts this, because I think they now recognize what CSA F280 actually tells you, and it is not the right tool in its current form to give you that yes or no answer on a cooling requirement. I believe that the folks in BC are going to be paying very close attention to what the National Building Code accepts for changes, and I expect that they will adopt similar language. But I think one thing that is also really important to keep in mind here is that there has to be some sort of guideline or standard to model refuge rooms and determine what the results are with the CSA F280 calculations and when it is actually telling you that cooling is not required.